Isolate. Hey there.
That's funny. He's gonna laugh pretty hard, I think. All right. Anyways, the answers to this. Who knows? 29. 3. Conversion of matter to energy. Yes, it's a common Regents question. That's what makes nuclear so powerful. Okay, you heard me go on and on about that yesterday. So that's why nuclear is unique, and it's a separate kind of branch of chemistry. Very, very unique because you're messing with the mass, which is in this question they use matter, but they take the mass of the nucleus and convert that. When I say they, I don't know what I mean by that. The atoms convert all their mass or some of their mass to energy. So remember that mass converted to energy, which is why the products will have a lower mass than the reactants. So that's another way they'll ask that question. Okay, this is maybe a little bit easier. 30. Atoms of iodine-131 spontaneously decay when 4. Unstable nuclei emit beta. How do you know it's beta and not alpha?
Table N.
Table N, very good. Go to table N for me. Someone tell me, what is the half-life of iodine-131 and tell me what that means. What is the half-life and what does it mean? So on table N, you look up iodine-131 and you see there's a B minus, right? That's why, Emily, you got it right, because it's a beta that's being emitted, so it's beta decay. Go ahead, Morgan.
It's 8.021 days.
8.021 days. You know what's interesting about that? The previous edition of these reference tables. So, someone look at the front. What is it, 2011, 2012, 2010? 11. So before 2011, the half-life of iodine was 8.07 days. So iodine-131 is a natural substance. So how does the half-life change? I found that interesting. Kids ask me that question because sometimes I'll have notes based on older half-life numbers, and I wonder why they change. It's very interesting to me. I actually don't really know. I haven't thought much about it, honestly, but really, you have an idea?
Maybe they weren't very accurate at first and they've gotten more accurate.
That would be the only explanation I could think of, yeah, is that whatever techniques they use to measure it, they've gotten more accurate, so, or less accurate.
Probably not.
Probably not, but you never know. Okay, anyways, just wanted to share that with you. What does that mean? What's the half-life mean?
Means the amount of time it takes for half of the sample to decay.
Right, so if you have 100 grams of iodine-131 after 8.23, 8.21 days, you would only have 50 grams. Where's that other 50 go? Laura?
It changes into something else.
Good, change it into something else. We're going to make sure we really get that today and we'll talk about it. So anyways, unstable emits beta particles, very good. So look, 2 questions in the first 30. Like I said the other day, you will have at least 2 to 3 multiple choice, I would think, with nuclear every single year. And kids usually do a good job with that because they ask kind of big topic questions like matter converted to energy or mass converted to energy. That's kind of a big concept. Unstable emits, beta. Look it up on table N. So these are kind of like not super technical questions, I don't think. So you guys should be, doing well with these warm-ups. I hope so. All right. Speaking of warm-ups, do any of your teachers use Kahoot?
Yeah.
I think I'm going to start doing that because I found out about it. It's pretty cool. So, so for warm-ups, maybe next week, I'll try and get this rolling. Just something like this, 2-3 questions, just something kind of a little more fun than just doing the Regents ones up here. So we'll see. If I get to it, we'll do it next week. But I do want to give that a shot. Does anyone not know what I'm talking about? Okay. You guys have smartphones? Okay. So you just go to kahoot.it, I think, and I make like a mini quiz. And we put it up, the questions come up here. It's kind of like a competition, sort of. And you have to pick the answer on your phone. And then it puts the top 5 scores up on the board. And then that's it. It's just kind of fun. It's just like a mini quiz that you do on your phone. So anyways, I want to start trying to do that once in a while. All right, test together. Compare your answers to your homework. stay focused.
Actually got it.
I am gonna send Slade a message here. Slade, don't graph the lab by hand. We're not gonna do that. Talk to me Monday. Earl wanted me to let you do it even though we're not going to do it. I just wanted to share that with you.
I never said that to him. I'll listen to him.
You gotta be careful. These things get kind of crazy. Gotta keep it professional.
Yeah.
All right. Maybe 1-2 more minutes tops. You guys good? All prepared? Same answers? Yes. Yes. Mamba, how are we doing?
I mean, I'm not really concerned about
So, with your 2 lines, did you finish this up? Okay. No, it's too today.
Oh, yeah.
Oh, similar, but your arrows do wrong. So what happens is you have a nucleus that just spontaneously gives off radiation. So you write the nucleus and then the arrow and then 2 blanks. So just like this one right here. Nucleus, whatever it is. So neon 19, arrow, and then 2. One of them is the radiation, one of them is the transmutation. I'm going to go over it anyway. Go ahead, Steve.
Okay, I'll let Okay.
All right, you 2 can keep working. Just keep going. Everyone else move back to your desk. All right. So, number 1. You know what? Here's what I'm going to do. I'm going to go through and tell you what each one represents, and then we'll go through the answers, right? Just so it'll kind of help you understand a little bit more. So number 1 on the top here, that's natural decay. Why is it natural decay? Because you have one element decaying into 2 other particles. So you have radium, arrow, radon plus alpha. So that is how you identify natural, is when you have just one substance on the reacting side. So just 1 means it's natural. If you see 2, like number 2, aluminum plus alpha, that's artificial, because you have an alpha particle interacting with the aluminum. That doesn't happen in nature on its own. There's not alpha particles just flying around randomly smashing into things. Okay? So that's something that scientists have to do. So number 2 is artificial. 3 is artificial. 4 is artificial on Earth. The sun does it naturally, but when we say natural and artificial, we mean on Earth, not the universe in general, okay? Or the galaxy, or solar system for that matter. We just mean Earth. So 4 is artificial. 5 is artificial. So the only natural transmutation on there is number 1. You guys, Laura, Hannah, and Bree, cease and desist there. I think I said that right. Just so you can listen to what I'm saying. Did we figure out one of them?
Yep.
Okay, good. Hannah helped a little bit. Thank you. All right. So let me just repeat this so you guys got it. Number 1 is natural. 2, 3, 4, 5 are all artificial. Again, natural means one element decaying into something new, transmutating, and then giving off radiation. So number 1 is natural. Number 1's also alpha decay, because it gives off an alpha particle. Number 2, not much else I can say about that, artificial transmutation. Number 3 is fission reaction, nuclear fission. Number 4 is nuclear fusion. That's what we learned about yesterday. And then 5 is fission as well. So 3 and 5 are nuclear fission, 4 is nuclear fusion. And then there's some other random questions here, so let's go through this. So 1 is 4, 2 is 1. Really, that's the only one. For question 2, which is alpha decay, there's only one alpha decay, and that's number 1 because it gives off an alpha particle. Yes, if you look at 4, it looks like an alpha is being produced, but that's not decay, that's fusion, it's different. And that's technically helium, not alpha. What's the difference? A whole bunch of, I'm not wording that right, a lot of alpha particles is helium. Just one is alpha. So 4 is not alpha decay, it's fusion, it's different. 3 and 5. 4, artificial would be 2, 3, 4, 5. 2, 3, 4, 5 are all artificial, 5 number 1. 6, nuclear chain reaction, that's fission, 3 and 5. The fission is the nuclear chain reaction. I showed you the video of the atoms all exploding there, or the nuclei. 7, which reaction releases an alpha? Again, the only answer is really 1. Because number 4, that's helium, it's a little bit different. Fusion is different than regular decay. Produces phosphorus, number 2, that was easy, should have been. 9 should be easy too, 5 produces strontium. And then 10, which 3 reactions produce noble gases? I guess technically I wrote this wrong. It's really only 2. Number 3 produces krypton, that's a noble gas, and number 4 produces helium. Again, number 1 really isn't helium, so I made a mistake on that one. So number 1 doesn't count as helium, that's alpha. It's different. So 4 and 5 are 3 and 4 are the only ones producing noble gases. So what was I hoping you got out of this? Can you identify natural decay versus artificial? That's the most important skill from this worksheet. Then, the second most important, I would say, is identifying fission and fusion. So what's natural, what's artificial, and then what's the difference between fission and fusion? Can you pick it out on paper? Because you won't ever have to write out those reactions, but you will have to answer a question, which of the following is nuclear fusion? Which of the following is nuclear fission? So you need to at least be able to identify it. That's why I gave you the worksheet. Questions on that? All right, flip it. So, neon 19, thorium 232, and krypton 85. You have to go to table N to do this. I don't think I told you that yesterday, so hopefully you realize that. So when you go to table N, Shane, what decay does neon 19 undergo? Positron. So what happens here is neon 19, you got to put 19 over 10. Arrow, because it naturally decays. Table N is all natural radioactivity, all natural decay. So neon gives off a positron. How'd you know that?
I went to the neon on table N and had the data part figure out the symbol with the plus.
Right, so the B plus. Right, the B plus. So, oops. So he looks up on table O, 0, positive 1. If you label the B instead of the E, that's okay, as long as you have the numbers. Okay, the E isn't as important as the numbers are. Okay, so 0 plus 1. Now we have to make a balance. Top number 19, bottom number 9. Look over there. Who's number 9? Fluorine. Okay, so that's the first one, neon 19. Questions? Thorium 232, TH. 232, what is it, 90, I think? Yeah. Mackenzie, what type of decay? Alpha. This makes sense because neon's small. It's going to give off beta or positron. The big ones, heavy ones, give off alpha. That's typical. Who can give me the missing element here? What is thorium transmutate into? Question. Give me the numbers. This one's 86, right? Yeah. And
88.
oh, so you mean radium?
Yeah.
That's fair. Oops. Honest mistake. Come on. All right. Yep.
And then 228.
228. Very good. 228. Again, the numbers have to balance. 232, 232, 90, and 90. Questions on that? Okay. And the last one. So the next one is krypton 85. KR 85. Krypton is number 36. Kaylin, what decay does it undergo?
Beta.
Beta, 0, -1. E, go ahead, finish it off there.
85 over 37.
RB, rubidium, there it is. There it is. Which one of those on the back is the most unstable? Neon 19, thorium 232, or krypton 85? Which one do you think is the most unstable? I haven't like taught this. Let's see what you think. Which one's the most unstable? Any ideas? Maddie? Why? Yes, neon, shortest half-life, means it decays very quickly, which means it's very unstable. If it decays quickly, that means it's giving off radiation very quickly, which means the nucleus is more unstable than the other ones. Does that make some sense? If something has a, like uranium-238, look at the very bottom of that chart. What's the half-life of U-238? It's like 4.5 billion years or something. Right? Isn't it 4.5 times 10 to the 9th or something like that? Years? Yeah. Pretty stable compared to something that decays in seconds or minutes. Does that make sense to you guys, I hope? Okay, so just keep that in mind. Half-life can tell you a lot about the sample. All right, you can put that away, take out your notes, keep the reference tables out. I'm just going to summarize fission and fusion real quick, and then we're going to learn about, I always forget this, 5 isotopes used in society for different things. And I'll explain what that means, because those are the 5 the regents could ask you about. Then we'll talk about half-life, and that's all we'll have time for today. Then we're done with nuclear in class. So Monday we're going to start talking about solutions. So that'll be good. All right, fission and fusion. Which one do you think is more beneficial to society? Fission or fusion? Based on what I said yesterday. Anybody have a thought on that? Oh, and you're in luck. I have some light reading for you for the weekend. Maybe you can call Slade and read this to him over the phone or something. You guys can talk on the phone or just text all the time? You talk all the time?
I don't believe that.
I talk much less on the phone than I used to. So you guys probably literally never talk to each other. Anybody call their friends to talk to them, or you just text? Or communicate through social
That's some
media?
really juicy gossip I call them.
Oh, okay. All right. Can't trust it to the interwebs. I want you to read this article from Monday. And it's very short. And you just might have a little quiz on Monday on the article. Otherwise, how am I going to really know you read it? This is something I've been wanting to do all year, but I kind of haven't been here. Scientific reading is important. Helps your brain. It's a different type of reading. It probably will improve how you do in other classes as well. Just in general, you get smarter in life the more you read. So scientific reading you don't do very often. Now this isn't a scientific journal or like an abstract of findings of some research, but it's about nuclear fusion. So it's very appropriate. So read it for Monday. I'm going to give you a couple question quiz. I don't know how many. So that's how you will be accountable. So please read that. It's pretty interesting, actually. I've told you about it. I just wanted you to read it. All right. So that's that. I'm not going to give you anything else, I don't think, over the weekend. So back to the question. Fission or fusion, what's more beneficial? What do you think?
Fusion.
Fusion, why?
It has
No waste of any kind. Yeah, I think it's kind of a no-brainer. Except you could say fusion probably, I don't know, but probably costs more than fission reaction. So a fission power plant costs a lot of money to run and upkeep. This thing here, for example, cost, it's there somewhere, a lot of money.
14 billion.
$14 billion. Where's that? In front? Hey, there it is. I know it's there somewhere. 14 billion. That's a lot of money. So, but that's because this is like the first of its kind. It's kind of like when something new comes out. Think of anything, a phone or a tablet, whatever. It's always more expensive, and then after a couple years, or there's more products that are similar, the price drops. So hopefully this doesn't cost 14 billion the rest of the time. Mr. McConnell? Oh, next one.
Yeah.
All right. Yeah, we We may finish the epicenter today, I don't know. So anyways, yeah, I just wanted to make sure we talked about that again one more time. Fusion doesn't have any waste, but it is really expensive because it takes so much energy to push those nuclei together. So that's basically the difficult part. Fission also produces a lot of energy, but you have your toxic waste, your radioactive waste, we'll call it, and that's something we have to deal with sometimes for years and years. So just keep that in mind. Sometimes the Regents talks about pros and cons or a negative or benefits. So in general, it's the waste and the money, that's your negatives. The positives, lots of energy, no pollution for the environment, either one of them. So that's a good thing, obviously. And you have your reactions, and we're moving on. All right, so 5 isotopes that are useful. So 5 useful isotopes. There's more than these 5, but these are the 5 that you might be tested on, so that's why we talk about it. First one, iodine-131. I-131 is used to detect thyroid problems. Now there's also an iodine, I think it's iodine, yeah, radioactive iodine that people don't necessarily eat or ingest. I don't know, I forget how it works, but yeah, I think they ingest it. And it can also shrink thyroid. So if some people have overactive thyroids or the thyroid's too big, they can try and shrink it with radiation. And it's an isotope that people take. And you're actually radioactive for a little while, a few days. But usually what ends up happening is it kind of destroys the thyroid, then those people have to take thyroid medication the rest of their life. My wife is one of those people. It's very common. It's a very common thing where people have overactive thyroids. So I don't think she'd mind me sharing that. Hopefully not, because it's on video. You know, she's doing well now, but it's kind of a tough thing because your thyroid regulates like everything in your body. But anyways, this is a common, very, very common isotope used. I don't know if 131 is the one they use to shrink it and the one they use to detect. I really don't, but it's still radioactive iodine. So the way I tell kids to remember this, iodine, thyroid, I don't know, sort of, maybe, okay. Technetium-99, used to detect brain tumors, I believe. Yes, detect brain tumors. So different type of scans, you know, I don't know all the scans off the top of my head. You know, there's PET scans, there's brain CT scans, there's CAT scans. So there's different types, there's boron scans, all types of different scans. So detect brain tumors. So again, like that video, you have to put these things in your body and they send out radiation depending on where in the body they pick it up and they can see what's going on. So that one's used for brain tumors. Oh, and liver disorders apparently, but they never really ask about that. So brain tumors and liver disorders. Cobalt-60, treat cancer. So that's radiation therapy. So if you have a tumor somewhere, you can blast it with radiation from a cobalt-60 nucleus. I know a long time ago, my dad actually went through this, and St. Peter's where he had it done. Cobalt-60 is what they use. I remember asking them because I actually had I hadn't started teaching yet, but it was right about the same time I started teaching. And I asked, you know, what isotope do you use? I mean, that's not a normal question. They were like, why do you want to know that? So anyways, that's what they used. And yeah, you basically just blast the tumors, hopefully shrinking them until they can be removed surgically. Yeah, I don't think this can shrink them to the point where they disappear, but you shrink them so it's easier to remove. So that's cobalt-60. Uranium-238. This one's kind of an odd one. It's used to date geological formations, and that's what I have written in my notes. So I think, you know, in general, non-organic material like rocks and such, so inorganic things, minerals, you know, dating how old this rock is, for example. I'll be honest with you, I don't know exactly how that one works as well as the next one, which is carbon-14. Carbon-14, just going to put it up here. carbon-14, and I have a video to talk about this. Carbon-14 is for dating organic material. So that's pieces of paper, newspapers or like artifacts, things that are found that have organic material or fossils. That's carbon dating. So the video, if I don't have time today, I'll show you Monday, even though we're starting a new unit, to explain how that works. All right. So those are the 5 isotopes we talk about. There's more. I have all this stuff on radioisotopes used in medicine. So if you're interested in this kind of stuff, nuclear medicine is kind of a big field these days. You ever hear of a nuclear stress test? You can do that to take a look at your heart. There's different scans for that. You drink a radioactive dye, or they inject it, and they can see how the blood, how it flows through your arteries. So PET scans, CT scans, maybe some of you have heard these things. Positron emission tomography, that's the PET scan. Just throwing some things out there, things you might have heard of. Radiotherapy. I wish we had more time. We could talk about this more, but we don't. Targeted alpha therapy, boron neutron capture therapy. So there's all types of different scans that involve radiation. Some of these we talked about. There's tons that I'm sure I don't even know about. But a lot of this is very useful, not just dangerous, right? It's very useful to help detect disease or tumors or something wrong with the body. So that's just important to know, right? You should know that. It's not all bad. All right, questions with any of these? All right. So, last but not least, half-life. I'm going to give you a little bit of notes, and I would like to show you that video today to kind of wrap up the nuclear stuff in class. Lab, we're going to continue. So let's define half-life. Make sure we know what the graph is supposed to look like, how to read it, and then we'll maybe do one sample problem of a half-life problem, a typical Regents half-life problem, and then that'll be it. So, who can give me the definition of half-life? What is the half-life of a radioactive isotope? What does that mean, the half-life? I know you know, but we're going to have someone else share. Ariana, thank you for volunteering. I'll start it off. The time? Good. The time it takes for half of the mass of a sample of a radioisotope, right? It's got to be radioactive. Radioisotope to decay. Time it takes for half of the mass of a radioisotope to decay. And I like to use the magnets to demonstrate this, kind of like that video, because I think it really helps. So you can try and draw this if you want, or just watch, whatever floats your boat. So let's say these are all atoms of some sort of radioisotope. I don't know, pick any of them on table N, it doesn't matter, okay? After a certain amount of time, so let's pick one so we have something to talk about. Someone pick one on table N. Just shout it out. What? Nitrogen what? N16. So nitrogen 16, what's the half-life?
7.13 seconds.
So nitrogen 16, half-life is 7 point what? 13 seconds? Okay. So this is very, very fast, very unstable. But what happens, this is a hard one to kind of understand, but what happens is, let's say we have, how many do we have? 1, 2, 3, 4, 16 atoms, right? So we have 16 nuclei of nitrogen 16. After 7.13 seconds, half of these don't just disappear, and it doesn't instantly happen at 7.13. It happens slowly over those 7 seconds. So what does that mean? The first half a second, this one will transmutate into something different. Then this one will transmutate into something different. And what happens is it does this over the course of 7 seconds. This is why this one's hard. Good one, Morgan. This one's hard to kind of understand, but over the course of those 7 seconds, half of the nuclei randomly will turn into something new. It's not like just half, like this chunk turns all at once. It's kind of one at a time, like that video. So if we do this, then this one turns, then this one turns, and I keep doing this until half of them turn, right? So we turn this one here. So we got 1, 2, 3, 4, 5, 6, 7. We need one more, right? 8. Does that make sense? 1, 2, 3, 4, 5, 6. Yeah. So that would be what it looks like at 7.13 seconds, because half of the nuclei randomly turned into this. What is this? You'd have to figure it out. So you go to table N and you'd say, all right, nitrogen 16. So N16 over 7. What's the decay mode? What does it decay? What does it release? What type of particle? Beta? Yes? Beta? Okay. So 0, -1e. Top number 16. This is oxygen. So what happens is over 7.13 seconds, half of them now are oxygen. So oxygen is the red one. Nope. Oxygen is the green one, sorry. Nitrogen was the original. So we still have 8 of those, and we have 8 of those. What happens when another 7 seconds pass? So another 7.13 seconds. How does this change? Because right now the ratio is 1 to 1, right? You have 8 of the nitrogen, so it's 8 to 8 right now. What happens after another? So 14.26 seconds. How does this picture look different? Anybody? Do you understand why these turn color? Some of you. Yes, because they went through natural decay. So this occurred. So every time one of these red ones turned green, it gave off a beta particle, right, in the analogy here, and it turned into oxygen. So I have half of the original sample. After another 7 seconds, how does this look different?
Ratio changes from 1 to 3.
Right, so we have to now, there's 1, 2, 3, 4, 5, 6, 7, 8 of the red, 8 of the green. So 4 of the red ones, another half of them, right? Half of 8 is 4. So 1, 2, 3, 4. So now we have 4 of the red and we have 12 of the oxygen. After another half-life, let's say those 2 decay. Now we only have 2 and we have 14. Right? So, no, 16? Did I do the math wrong there? What did I do wrong?
No.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14. I was right, 14. So, yes, that makes sense. So, that's how half-life works. It doesn't just disappear. It turns into something new, and this is the best visual I can give you of how it works. Notice how, as time progresses, your mass keeps cutting in half. That's what half-life is all about. Yes?
Does it ever fully convert over, or is it like one of those things where it just keeps getting smaller?
Keeps getting smaller and smaller and smaller and smaller. That's why the graph, that was the next thing we're going to put in our notes. Good question. Not sure we'll have time for the video, but here, half-life graph. So a half-life graph, which we're creating in lab, so sketch one in your notes here, where we put mass on the y and time on the x. And what it looks like is something like this. So it starts to level off, sort of. It'll continue to go down and down and down, but it'll never really touch that axis. So the mass continually drops as time increases, right, as time passes. And it's important to understand how to read this. Let's say our starting mass was 100 grams, okay? So let's use this example, nitrogen 16. So 50 grams, let's say, is right here. So if this was nitrogen 16 we were graphing, right here, we drop this straight down, according to this, what time would that be? Where you have half of your original sample for nitrogen 16. What would the time be? According to table N, when does this lose half of its mass? How much time? Again.
7.13 seconds.
Yeah, 7.13 seconds. And then another half would be 25 grams. And then we go over here and drop it down. That would be 14.26 seconds. I know it's kind of small to see. The point is, that's why the graph looks like it does. It cuts in half, then that gets cut in half again, which is a smaller change. That's why it has a slope. It's not straight. The time keeps increasing. How does it increase? By half-life. So 7.13 plus 7.13 plus 7.13. So the time is going to be consistent. The mass is going to change a different amount as it gets smaller and smaller and smaller and smaller. So if this is confusing, that's okay. We're going to do more in lab with this stuff. But I want to do at least intro in class, get the definition, do the magnet thing here, draw a graph, but we're going to do more practice in lab. I think what I would like to do, if I have time, hold on, don't pack up. If I can get you this video here, how long is it? Oh, it's only 2 minutes, yeah. So instead of giving you any more notes, I'm going to stop, and this is going to explain how carbon dating works, because I think you should know how it works. So don't forget that article, and this video should put us at the end here. Someone get the lights, please. It's going to be tight. If the bell rings, I'll just have to show you again on Monday.